Alright, so for this project there wasn't really any brainstorming. We just kind of followed instructions on the packet. So to begin, we were to design this 3-bit mod 6 up counter using D flip-flops, and basically what it's supposed to do is it's supposed to count from 0 to 5. And so the way that we did that is we used 3 flip-flops, just kind of in the same way that we did the activity 3.2.1, except inside this one, instead of using a hex display, we used a 7-segment and a 74LS47 encoder. And so basically how the hex display kind of was able to convert binary to number just by itself, because we're using a 7-segment display in this one, we had to use the 74LS47. And there's a bunch of resistors connected between that just because we don't want to fry anything, so and that's just the way that works. So and then in order to make it reset at well, in order to make it count to 5 and then go back to 0, there's this NAND gate down in the bottom right hand corner of those flip-flops, those 3 flip-flops, and its inputs are the binary number for 6. So when 6 goes into that NAND gate, or when the binary number of 6 goes into that NAND gate, the clears, the outputs of that NAND gate, are going to all receive a 0, and that's going to reset the whole thing, and it's going to go back to 0. So that's how that one works, and I've got a video, it's working, so there's that. And then we were supposed to modify this circuit so that it would count from 2 to 6, and it's a little bit different on this one because instead of counting, instead of counting to 5, it's counting to 6. So we changed our inputs for the NAND gate so that when it reached the binary number of 7, it would reset. So it goes 1, 2, 3, 4, 5, 6, and then 7 it switches back to reset. And then in order to make it reset to 2 instead of 0, we had to switch the preset and the clear on the second gate, on the second flip-flop, and that's because it creates the binary number of 2, 0, 1, 0. So that's what we did there, and it works. So there's a video. And then after we created it on multisim, we were supposed to create it on our breadboards, and it got a little bit tricky. This was actually the most difficult part of the whole thing. Part of the problem was that our resistors kind of were having problems, and then at one point we were using an anode or a cathode, the one that didn't work, so we had to go back and switch our 7-segment display. And then it was just different because we used different gates that we weren't used to, like the 74LS47 and which is the encoder, and then the 74LS74s, which are the flip-flops, and we just haven't worked with those before, so that's why it was a little bit different. But we got it to work eventually, and we've got video of that to show. And then it just made the lights. There was a light that blinked to show us that our clock was pulsing correctly. And so there's the video of 0 to 5. And then there's there's another video of 0 to 6 or 2 to 6. And then after that, we were to put it on the what are they called? PLD format, the digital logic boards, DLBs, that's what it is. So we had to draw our design, redraw our design on multisim and PLD format, and that's just what this looks like. So basically the same thing except just slightly different icons, and then we just uploaded it up to the boards and it worked. This one's 0 to 5, and then we have our 0 to 6 following that. And that should be about it. That's the way that we did our project. Conclusion, it was pretty cool to be able to go through the entire process and see how it worked on every step. I was able to understand flip-flops a lot better by the end of all this, especially considering at the beginning I didn't really know. I understood what was going on a little bit, but I couldn't really explain it. So after seeing how it works throughout this entire thing, it's cool to just be able to see how it works on all the different media types. So there we go, 3.2.2 and 3.2.3. That's what we did.